So I don't have the instruction set up, but basically, okay, so you see Tien set it up so that we can run different steps. So you will be running import. And after import, you see this view, right? If you see a mobile view, then you see the macros and the logic, and then you place the instances. So you place the instances, then you'll go into the layout view, and you're going to see this view. So all the all the macros already placed. And over here, you want to turn off this annoying, it's called terminal here. So when you turn it off, you'll see this, what you want to see. Then you run the placement adjustment. This, you guys already went through this, so I'm not going to go through this anymore, but just to set up the stage. So after you run the that placement, you see this view. So everything is adjusted. The die size already what you wanted, and now you have a view. And I'm going to turn off the blockages. So now you have this view. So everything is there. So now you're gonna go add a power ring. Right? So you can tell I'm not as fancy as Tian in terms of getting all these files. But so you see in here, connect power net, right? Connect global net VDD, type PG pin, type high and low, right? So yeah, and then VDD, this pin-based name, meaning that the pin on the should I so these are VDD, right? You can, yeah. So what we're telling is that the name on the VDD and ground is those names, right? So you say base of VDD and base is VSS. And the net is VDD. So see this net is VDD, net VSS. So connect all these things to all the things that have the pin name. Connect this net to all the pins that have a VDD VSS. And then you connect the type low and type cell high to this net. So after you do this, you can tell there's nothing here because you only do this one as a logical connection. Right now, let's turn on the pin. So when you do the pin object visible, that means that equivalent of you go in here and you do cell and you turn on the pin shape, right? On, off, right? Off, on. So in pin shape here, you can tell that internally there's already a ring in. This is a pin on the macros. It means there's already an internal ring. but now you're gonna add to it. So I don't know why they're gonna do that, but that's what we're gonna do. So you're gonna add to it. You see in here, you say you're gonna add rings, and a lot of things are really I don't pay attention. So things that we pay attention is here, right? You say stack via top metal 9 metal 1, meaning that if I create something and it run over top of anything, above metal one and above, I'm going to veer down, right? And then go exact crossover side. I think crossover means, intersections. There's a lot of these things you can do a man, right? If you're curious, you can do in here. Tian probably already told you, right? You can do a man here. And then you can say, hey, this is an attribute, but you can still do a man on the attribute, and then it will tell you exactly what it is. But for the sake of time, we're not going to worry about that. But this is a command add ring, right? So we do the setup, and then you add ring. So let's talk about that ring. You see here, you find that the net, there's an empty in the net. So I guess this one will create some errors. I think it's intentional, but let's see if it does that. See, it's invalid net names because there's nothing you put in here. So what you do is that you run the next one, which has a right. Hello? Okay. So next one, you do it again, and then you give it this net name VDD VSS, you see here. So you're going to run again and see what happens. So now it's not clear, but you can see here a ring has been added. But if I turn off the pin shape, it's obvious. Right? So there's no, you do a full, you see this ring is added around the core, right? So the ring, like you want metal 8 left and right, metal 9, right? So this is metal 8. You do a Q, hello. Um, then you see it's metal 8 right here, and it's connected to VSS, right? So it's over here. So it does what you need it to do. So you can play with this and play with the numbers and to see how it's built. So basically, you see where where these little these are the rows, right? This is the core. This is the edge of the core. It builds off this one and with an offset and the distance and the width, right? And over here should have all the vias. Yeah, you see this one is all the vias in it. So that's the coring, and then next what it does is I think I did it too. So I did the coring, and then the next one we do the block. So first of all, you need to make sure only the selection of the blocks that you want. So first of all, you should deselect in case you click on an IO cell somewhere. So to be safe, you want to deselect it all, and then you select is memory is black box. So meaning that all the macros, right? If there's a black box here, you want to select them too. So you're going to build a ring around each of that. So now you can see they are selected. Okay, forget about the flight line. But over here, you set up like metal 9 to metal 1, crossover similarly to that. But in here, you see, I forgot to mention again, block rings. So over here, you see type core rings. Over here, you type block rings, right? And then you say top metal 9, left right metal 8, similarly to the core. And the width, top, you can do one for all, but or you can be specific for top bottom, what width you want, left right, and offset, and different control. So this one you're gonna just build the block rings. Right? Uh, so um, so you build that block ring, as you can see over here. You see now you have this. Let's go over here. Now you see the ring around each block, right? Like I mentioned, sometimes it just smartly, share them, right? So that, and yeah, over here, yeah, they share. But if you turn on the pin shape, you can see internally it already have a ring. So it's kind of an overkill. Maybe it's not. Maybe it's still good to have a main ring here and then connect to the sub ring, because you go, yeah. Oh, wrong way. Yeah, you see, it's just like routing of đi thủy lợi or whatever. You want to distribute water here, then you have the main feed, and then you distribute the juice over. So and if there are questions, please ask me, because I think this is so simple that we probably finish with a lab very fast. And then there's another add ring, block ring around selected. I don't know why we have this similar thing. What does this one do? I don't know. I didn't pay attention to this one. See what it does. Oh, I see. I don't know. Error, right? So it's just meant to be say, if you don't do it right, it will be error out. So that's building the ring, right? So so it's very straightforward. And then let's build the stripes, right? So okay. So what does it do? So add a power stripes. You can see here it will be metal 9 horizontal, and then width and every other details like width, spacing, everything. And with the set DB first, and then add stripe later, and see what it does. So now you can see the horizontal stripes, and let's turn off this pin shape. So you see horizontal in metal 9 being built, right? So it's just horizontal. So it did connect to whatever, you see when the metal 9 is connected, it's C metal 8 here, so it just connect already. VSS connect to VSS, VDD connected to VDD. So it see the pins here, even in the pin, it see the pins here, and pin here is a different layer. It may be metal 2. So if we are down from metal 9 to metal 2, so that's what this strip, horizontal does. The horizontal stripes, and then we have the next one. What does it do? Yeah. So next one is say do metal 8 for me vertical, right? And with all the width and spacing, etc. So it does this. So pretty straightforward. But the important thing is that you need to understand what these are for. We're going to analyze them, why they're needed and all. So metal H here, so you can see metal H is built vertically. So some of them already there in the ring. Now you have metal H go, and then you see whenever metal H cross metal 9, it it veers to the metal 9, right? So metal H just added, but if VSS is see a cross section VSS, it just put veers in here, right? You see veers. So and then try to see if we have yeah, over here we don't see the standard cell yet. And then you write the DB. I don't know if this is needed or not, but so that's the stripes or straps, right? Vertical, horizontal. You can see they build in pair, right? So now in the standard cell area, you have this grid. You have this grid, and Friday you see how this grid is represented in terms of resistance and current taps, and how they are analyzed, and the IR drop to all these different locations, how they analyze and making sure that they meet all the requirements. So that's the grid. This stripes mainly is for the standard cell area. Right. It's a regular grid. And then you do S route, special route. So what is it? So in here you see we didn't cover it yet, but basically it's a command called route special. Is a special router. It's not the placement router, but say connect all the block pin, pad pin, and core pins together. So yeah, I guess the attribute that they put on when we have the cover, so it's used here. It's used in this size. The block pin, core pin, and pad connecting together, and have metal and 1 to metal 9. So the 2 nets and block pin use left, all these different controls that I didn't go through, but basically what this does is going to route. So you build the straps, you build the rings. Hello, it's not responding. Okay, then now you run the route. So let's see what it does. Right? You see, right over here, it has some additional shapes that the router just build these shape in metal 3. And this is so metal 4 in yellow, and this is VSS. You see VSS. So go here and then they go here, VSS. So you see pad VSS. Let me just zoom in here. So a ton of VDD, pad VSS 8, VSS 7, VSS 6. So it route from the ring, right? It have a special router to route the pad pin. Yeah, over here you see it said route the block pin, pad pin, and core pin together. So this is core pins, right? The shape it at is at an attribute called core pin, and then the round, the ring around the macros is called block pins. and then pad all these pad pins. So they just see the logical connections, and now they do all these shapes. So all these VSS connected to pad from the rings, right? And uh, so it looks like all the pound and ground. So you see VDD here connected to VDD. And it looks like it only needed to connect from the outside. Oh, maybe it did some of these, or maybe it did not. No, these are middle nine already added already. So it looks like it's from the pad it connect to the outer ring, the core ring, and everything is connected. So I think that's it for this this lab. I think that's all Tin has. Any question? Straightforward. So the important thing is understand the theory, and the lab should be straightforward. So at this point, we have half an hour. We're gonna go over the pre-assessment to see if anything else we need to address. So I'm going to kill this guy. So let's go over the assessment. We'll go over this assessment first, and then we'll go over the. Oh, I remember I owe someone a question of what determined the core. So let's see. Someone asked a question. There's a core of the other. Maybe I just use. I just use this one. So there was a question about the core to I/O, right? Spacing. There's a core to I/O spacing, and what determines that? And so, but I checked with the DRC-LVS guy here. Apparently, it's not on top of their head either. It's just something, if it pops up, you know what rule is violating. But since it appears that it is determined by when you build this power ring, you need to have a minimum space between the core and the I/O. So by the fact that you have a requirement on power ring, then that space is probably cover all the design rules. So it's not on top of our head in terms of what determine that space. So most likely it's going to be just the core ring itself. But I'm still trying to get the answer from our DRC LVS at Skyworks and let you know what they found out. So let's see. So let's go over the reassessment. So we have 66 responses, and you can see the difference. So why is establishing a power grid essential? So let me see what the responses are. That's actually only 12 got correct. And so to it, but maybe you guys can after we're done with the lecture, see if the response is better this time. So I don't want to do the poll. Maybe people just answer question A, B, C, D. And here, why is establishing a power grid essential? A, to distribute power to all cells on chip. B, to ensure signal integrity. C, to ensure reliable chip operations in all conditions. D, all of the above. Maybe just type in the chat to see what you think the answer now is. Just curiosity. Or actually, maybe someone can help me just put a poll on all these things, and we can have fun, interacted. Anybody? Oh well, the answer is to distribute all power. Huh? I think this is wrong. This should be all the above. I apologize. Yeah. I think Lê Thanh Trung, all of the above. This is inaccurate. Yeah, the answer is no wonder only 12 got it right. Okay. All right. Apology. Yeah, it's all of the above. Okay, so the answer is all of the above. All right. So keep on typing. What is the relationship between VDD on IO paths and core VDD? Right. A, VDD on IO paths is always lower than core VDD. B, always higher. C, can be either higher or lower depending on the design. And D, VDD on IO paths is unrelated to core VDD. This is not a very good answer, but please type in what you want, what you think, A, B, or C, or D. Just don't pick D. This is not very good answer either. So you can tell these are done in a rush. Nguyễn Đoàn Hoàng Phúc said B, always higher. B, always higher. C, Lê Thanh Trung, C is correct because we already have some question, right? So I would think B is a good guess, but like Vũ was saying, sometimes, PDD on IOPATH can be lower. So yeah, either B or C are acceptable answers. Okay, thank you for the answers. How does the choice of metal layers in the power grid influence electromigration in VLSI design? Right, the choice of metal layer. Oops, sorry. Sorry. What did I do? I reviewed the correct answer already. Yeah. A, metal layer selection has no impact on EM. B, thicker metal layers exacerbate electromigration risks. C, thinner metal layers increase susceptibility to electromigration. And D, proper metal layer choice can help mitigate electromigration concerns. What is the answer? Yeah, thank you, Nguyễn Nam Hải, Đặng Nguyễn Vinh Quang, Phan Trọng Nhân. Yeah, the answer is D. Okay. Thanks all for the answer. What is the primary purpose of a core ring in VSI design? Enclosing specific functional blocks, providing localized power distribution within the core, surrounding the entire core to ensure uniform power delivery, minimizing crosstalk between neighboring circuits. All right, the correct answer is C, yep. And I don't know this will be useful or I have to explain. I think the request to go over this is probably because I didn't release the the test result. When I release the score, then you see what the correct answer is. So I don't. So if we go over this and you need more explanation, then let me know. Otherwise, we just play the game again. Yeah, after you sit through the lecture. Maybe what is the primary purpose of a block power ring in VLSI design? A block power ring enclosing the entire core, minimizing voltage drop, ensuring stable power delivery within a specific functional block, enhancing clock distribution efficiency, providing flexibility in power distribution without focusing on circuit blocks. So the answer is B. Enclosing the entire core, no, we only should block, right? Minimizing voltage drop and within a specific functional block, sound good. It had nothing to do with clock distribution for sure, and it has to be around a block. It's not cannot be just regular flexibility. So yeah, the answer is B. Thank you. A lot of you guys got it right. All right. Is a block power ring always necessary? True, false. Enhancing clock distribution, providing that flexibility without focusing on the circuit block. Is it always necessary? True or false? B, false, right? Yeah, because that's correct. Because sometimes you already have a ring around, or sometimes you have the yeah. Is that this guy? Yeah. Yeah, sometimes you have a strap, then you just hook directly to the straps, and sometimes you already have a ring, you can connect to the ring without building the ring. So, okay, good. I think all of you got that answer. What components are typically connected to the core VDD? Only flip-flops and latches, ALUs exclusively. Core VDD is not connected to any specific components. Standard cells, flip-flops, registers, memory cells, and clock tree networks, among others. Awesome. D, yes. Correct answer is D. What can the core of a VLSI chip use the I/O VDD? The core requires higher voltage. The core is less sensitive to noise and interference. The I/O VDD is optimized for mixed signal interface. The core and I/O sections have distinct functions and voltage requirements. Yeah, a lot of you answer D. That's correct, right? No need to explain that, right? Because not always the core doesn't always have higher voltage levels. The core is not always less sensitive. I/O is optimized for mixing noise. Make no sense. Okay, what can the core of a VLSI chip use the I/O VDD? Oh, is that a repetition? Sorry. Which design consideration is crucial for managing IR drops for dynamic circuit switching? Clock trees, optimization, power grid density, via placement, decoupling capacitor sizing. So this one is not easy to answer. Let me see. Did somebody say D or okay? Right. So the answer is decoupling capacitor sizing. So it's very good answer for it, but we didn't go over that yet. So so basically, dynamic circuit switching. As we already went through that. Let's review that. I don't think we went over it. So I'm going to go over that next week. But maybe I can. Never mind. I'll go over it on Friday. Yeah, but yeah, basically the decoupling caps will play a very important role in terms of handling dynamic power issues. And okay, any question for maybe we can go over the lecture 6 question answer. I don't know if this is useful or not. You guys tell me. Any comments on the usefulness of going over the assessment? Oh, it's very helpful. Okay, I'm glad. Okay, so let's continue then. Let's see if the where's lesson 6. Maybe we go in lecture 6 pre-assessment. Yeah, you can tell these things we just winging it, but in maybe in future classes we'll be more prepared. The flipped classroom is really something we came up the last minute, so we still try and error. So we just come up with this, in a very quickly manner. And in here, there's 67, so it's good. Let's see what the distribution of the score is. Oh, sorry, we didn't mean to. Just I don't want to share the individual. So in here, yeah, most people got it right. So let's go through the questions. What are the main purposes of macro placement steps? Minimizing the total wire length, minimizing the length of the timing critical paths, optimizing area utilization, all of the above. Okay, cool. All right, D is above, is a correct answer. So all of the above, because minimizing total wire length, right? The macro placement, the the smaller when you do, you want to do for sure A. So a lot of people got A, a few got A too, but minimizing the length of timing critical paths, you can see, yeah, yeah. See, maybe it's helpful to get the. So maybe it's a refresh since we have time. So minimizing the the wide length, right? The length of timing critical path. We mentioned something about a DSP circuit. Hello. And here is an example, right? So this is just DFT is really timing critical, meaning in a DSP chip, that's the critical timing critical path. So you want all the blocks to be close together, including the arithmetic units over here. So when you have the signal doesn't have to travel far. I mean, it can be reduce the delays. So absolutely, that's part of the floor planning. So placement of these things affects the timing critical paths. Um, so optimizing area utilization for sure, because if you look at the standard cell areas over here, so by placing these macros, give a contiguous standard cell placement area. This is more efficient than you have fragmented and you see these notches. So these things is you can still route and you still can place, but the efficiency of it is not as good as this wide big standard cell area. So that's yep. That optimizing area utilization. So yes, is all of the above. What does macro placement contribute to time enclosure? No impact. It helps to improve the constraints. It minimizes the length of timing critical paths. It only affects area utilization. What is the answer? Say yes, Nguyễn Văn Duyên. Yes. Say yes. Say is correct answer. So there's no, yeah, because it does have impact on time enclosure. It doesn't help with improving the constraints. The constraints have nothing to do with the macro placement. Minimizing the length of timing critical path, we just went through it, and it only affects area utilization. Area utilization only one of them, but it can has more. So that's good. Thank you for all the answers. How does macro placement contribute to power distribution in VLSI design? Right. Improve by improving the speed, by optimizing the signal paths, by placing higher power macros closer to the power source, by fixing the right design rules. Yeah, yeah. So right. Improving is not it help improve the speed, but it doesn't. It's not related to power distribution. Help with optimizing signal path. Yeah, the correct answer is C. Yeah. Yeah, because by placing the high power near the power source, that means it's power hungry. Related to IR drop as well, right? So do we have a picture for that? So basically, if the higher power macros draw a lot of currents, right? So it will have impact on the IR drop along the way. So the closer it is, the less IR drop and the less impact on the SYN routing logic. What role does macro placement play in achieving a compact design? It has no impact. It improves hierarchical organization. It optimizes area utilization. It increases the chip operating frequency. So this should be an easy answer. Okay. So, yep, the answer is C. What impact can longer buses have on the signal propagation delays? Increase the delay, decrease the delay, no impact on delays, introducing clock skews. Yeah, increase the delay. Right. All right. How does minimizing wide length contribute to overall chip performance? Reduce signal integrity, increases signal propagation delays, improve performance by reducing delays, enhance clock skew. Yeah, the answer is improve performance. So it's C, not A, because minimizing wide length that reduce the delay. So the RC delays. What is the one benefit minimizing wide length of frequently switching buses? Longer clock skew, reduced power consumption, higher clock crosstalk issues, increased signal degradation. Yep, the correct answer is B, right? Reduce power consumption because when you switch the bus very often, so the longer the bus, the more RC, so the more power. So if you want to save power by making those buses shorter at the expense of some other buses, then you still gain because these buses switch more often than other buses. So you wanna give that priority. So how does reducing bus length contribute to low power consumption? It increases the dynamic power, raise clock skews, decrease wire capacitance, boost signal propagation delays. Yep, the answer is C, decrease wire capacitance. Right. So it has nothing to do with clock skew. It does reduce the dynamic power, not increase, or it doesn't increase the propagation delay. In floor planning, what is a chimney referring to? A narrow placement area between macros, area with excessive signal propagation delays, region with elevated power consumption, space intentionally left empty. Yep. Yep, the correct answer is A. Not C. C, the region with elevated power consumption. No, it doesn't always mean like it's it just look like a car, you know? So it's a narrow in between macros.
Phil,
What
we had a
issue?
question.
Yeah,
We had a
yeah.
question come in. Do all signal paths in the chip use bus configuration?
No, was a bus only, mainly the data paths like a program bus that holds the entire instruction like 32-bit, 64-bit instructions, or a lot of time our data paths like 32-bit, 64-bit data. But there are a lot of random logic that really have it's just single signals. Not all of them come in bus form. Okay. What issue is commonly associated with narrow placement areas? So increased wire capacitance, congestion and routing difficulty, reduced clock skew, improve signal propagation delays. Was an narrow placement area. Yep, the answer is B, congestion and routing difficulties, right? You see here, you have pins and you have signals coming in. You have hard time with congestion and routing. Yeah, doesn't have anything to clock skews, increase wire capacitance. I'm not sure. Improve signal for sure. It's not going to improve the signal propagation delay. What is the purpose of avoiding chimneys in macro placement? Decrease wire length, minimize clock skew, optimize signal paths, prevent congestion and timing issue. Yep, correct. Prevent congestion and timing issue. So it's obvious, right? That's good. Why are notches discouraged in VLSI floor planning? So notches are these guys, right? Notches. So to increase signal degradation, to introduce clock skews, to minimize wire length, to maintain uniform wire density and prevent timing issues. Yep, wire density, right? Uniform wire density and prevent timing issue. Why is a wire density? Right. So for notches like this, right? So over here, so wires are determined by the standard cell area. Over here, now all of a sudden you have signals that need to escape from the memories, in addition to the signals in the standard cell areas. So all of a sudden, wire density over here is more than wire density over here. So that's when you become, like cells have to be pushed out and critical paths are affected and congestions are here because you have more wires per unit area here. So you want to discourage that. It still can be routable, but it will affect your overall quality. Bum, bum, bum. How does the placement of macros impact the standard cell placement areas? It has no impact. It helps increase standard cell density. It can create congestion and limit available space for standard cells. It improves signal propagation delays in standard cell area. So what is the answer? Yep, yep. The answer is C. It can create congestion, like we were mentioned, right? It notches and also the areas here. Yeah, if you don't leave enough space for all these I/O to escape, it will create some congestion problems. And so that's easy to understand. Um, why my moving macros to the edges? Oh, we're running out of time. Oh, well, a lot more. Okay, I think we run out of time, so I hope that is useful. And I didn't realize that we have a lot more here. So, okay, well, out of respect to people have to make the next class. Thank you very much for all the questions and answers. And hope you have a good day. Sure, I'm glad it was useful. All right.